Welcome to Pre-Calculus. Today we'll be discussing graphs of rational functions. Some of the terms I'm going to be using often in this lesson are domain, limits, asymptotes, and intercepts. Having the variable on the bottom of the fraction is a problem because the denominator of a fraction can never be zero. Usually some domain value of x makes the denominator 0. The function jumps over this value in the graph, creating what's called a vertical asymptote. The graph approaches this point, but never reaches it. With all this in mind, I need you to find the values of x that you cannot plug into a rational function. Let's get started with a function we'll call f of x. To find the value of x in which the function is undefined, I need you to set the denominator of the rational function equal to 0. Solve this equation for x. In this case, it's a quadratic, so I'm going to try to factor it. And I'm going to find I have two vertical asymptotes. One when x is equal to -7, and the other when x is equal to 3. It would help to take a look at the graph of this function. As you can see, there's our asymptote at x equals 3, and this function also has another vertical asymptote at x equals a -7. Another characteristic of a rational function is the horizontal asymptote. To find a horizontal asymptote of a rational function, you need to look at the degree of the polynomials in the numerator and the denominator. The degree is the highest power of the variable in the polynomial expression. We're going to deal with this in three examples. Case 1. If the denominator has a higher degree, like an f of x, the horizontal asymptote is automatically the x-axis, or y equals 0. In the function f of x that we just dealt with, let's find the horizontal asymptotes, if there's any. In this case, with x as the degree above and x squared the degree in the denominator, it turns out we have an example of what I'm going to call case 1. Little degree over big degree. In this case, the horizontal asymptote is going to be the x-axis, or y equals 0. The last piece of the puzzle is to find the intercepts, or where the line or the curve crosses the x and y axis, if any exist. To find the y-intercepts of the equation, you set x equal to 0. To find the x-intercepts of the equation, you set y equal to 0. So to find the intercepts, the first thing I'll find is the y-intercept. In other words, I'll set x equal to 0. This thing pretty well disappears if I set x equal to 0, so it's going to be y equals 0 minus 1 over -21. So in other words, the intercept is 0, 1 over 21. The x-intercept, I'd set y equal to 0. Let's see, when I cross multiply, basically the denominator disappears. Add 1. Divide by 3, and the other intercept, the x-intercept, is going to be the point 1 over 3, 0. And that'll be my x-intercept. Let's try another example. We'll call it g of x. To find the vertical asymptotes for g of x, I'm going to set the denominator equal to 0. And it looks like I'm going to get x equal to 4/3. In other words, the function is going to approach 4/3 but never get there. Horizontal asymptotes are a little trickier than the rest. This is what I'm going to call case 2, an example of case 2. If the numerator and denominator have an equal degree, like in g of x, we must divide the leading coefficients, that is, the coefficients of the terms with the highest degrees, to find the horizontal asymptote. The function g of x has equal degrees on top and bottom. To find the horizontal asymptote, then, I'll divide the leading coefficients Now notice I'm going to have to rearrange this a little bit. The 4 minus 3x, I'm going to write that as negative 3x plus 4. And this means I divide 6 divided by negative 3, or y equals a negative 2. It would help to have a visual of some of this, so I'll tell you what. The vertical asymptote of, if you recall, 4/3 would look like this, and the horizontal asymptote of negative 2 would be this line. To find the intercepts of the function g of x, first I'll find the y-intercept by setting x equal to 0. This eliminates everything except the 12 and the 4. So 12 divided by 4, it looks like my y-intercept is going to be 3, or in other words, 0, 3 is the point. My x-intercept, I'll set y equal to 0. Cross multiply and the denominator disappears. Subtract 12, divide by 6. X equals a negative 2, or in other words, negative 2, 0. Okay, one more example. In h of x, first I'm going to try to find the vertical asymptotes. In other words, what will mess up that denominator? What will make it equal 0? So I'm going to set the denominator of x plus 2 equal to 0. Subtract 2 from both sides, and I'm going to get x equals a negative 2. That's my vertical asymptote. Looking at the graph, let's see, x equals negative 2 would be right about here, and that's an asymptote of this function. But I think there's something more interesting going on. This last example we're doing is an example I'm going to call case 3. If the numerator has the bigger degree of exactly one more than the denominator, the graph will have an oblique asymptote. Oblique asymptotes are neither horizontal nor vertical. In fact, an asymptote doesn't even have to be a straight line at all. It can be a slight curve or a really complicated curve. To find an oblique asymptote, you have to use long division of polynomials to find the quotient. You take the denominator of the rational function and divide it into the numerator. The quotient, neglecting the remainder, gives you the equation of a line of your oblique asymptote. This is a lot easier to understand once you see an example. So let's do one now. As I said, this is an example of what we'll call case 3 of horizontal asymptotes. The function h of x has an oblique asymptote because the numerator has the higher degree in the polynomial. By using long division, you're going to get a quotient of, let's see, x goes in x, it's going to be x2. This quotient means that the oblique asymptote follows the equation of y equals x minus 2. That's a lot easier to understand if you look at the graph. So this is a picture of the original function, and if we add the oblique asymptote, whose equation is y equals x minus 2, you can see the function gets closer and closer to this line, but never touches it. The last thing we need to find for our last example are the intercepts of h of x. To find the y-intercept, I'll set x equal to 0, which will leave me with y equals negative 9 over 2. In other words, 0, negative 9 over 2 would be the intercept. The x-intercepts I find by setting y equal to 0. I'd lose the denominator. I got a polynomial. I can subtract, add 9 to both sides, square root, plus or minus 3. So it looks like my intercepts, there's going to be 3 of them. 3, 0, negative 3, 0, and 0, negative 9 halves. The last topic I'd like to discuss tonight is when you're asked to use limits to describe the behavior of a function. Take a look at this, the very first function, this f of x function we had. If I approach one of my asymptotes from the left, that is, in f of x it was -7. If I get closer and closer to that, you'll notice that I don't actually get there, but I keep going down. So the value of the function gets less and less and less. It heads toward -infinity, I'm going to say. If I come at that -7 from the right, then the value of the function is going to get larger and larger and larger. It's going to go to infinity in the positive direction. A limit is a fundamental concept in calculus. If f of x is a function defined around a point C, but may not be at C itself, then the formal limit equation becomes this. The limit of f of x as x goes to -7 from the left, that's why that little negative sign to the upper right of the 7, then that means the function goes to -infinity. The limit of f of x as x approaches -7, one of its asymptotes, from the right, that's why the plus sign's there, you'll remember the function goes to positive infinity. Now let's take a look at that other asymptote. As I approach 3 from the left, I go to -infinity. As I look at the right limit, coming in from the right, the function goes to positive infinity. Okay, so what are left and right limits? When a function is not defined around some point C, but only to the left or to the right of point C, then the limits are called the left limit and the right limit at C. In this case, the limit of f of x as x approaches 3 from the left is equal to -infinity. The limit of f of x as x approaches 3 from the right equal to 3 with a little 3, not indicate a positive 3, but indicate I'm coming at 3 from the right, is going to be positive infinity. In h of x, our vertical asymptote was at -2. You can see if we approach that from the left, the limit of this function as we approach -2 from the left is positive infinity. As we approach it from the right, it's -infinity. And I need you just to be able to write that out formally. So the limit of h of x as x goes to -2 from the left is positive infinity. And the limit of h of x as x approaches -2 from the right is a -infinity. So in this lesson, we discussed the graphs of rational functions. We figured out what domain, asymptote, and limits mean. And we finished up with some examples of limit notation. Here endeth the lesson. Thank you for your time and attention.